Okay, so today we're going to talk about generalized linear models. And this is the type of modeling that you'll be using to do your final project. And of course, there's lots of different types of models we could use, particular for the sort of supervised learning. Why generalized linear models are interesting is because they have some sort of nice properties in terms of fitting and also analysis of the quality of the fit that lends some interpretability. So it's a sort of nice way to, accept that you're not going to know every type of modeling in data science, but when you come to the address component, there's a type of model that you can look at and understand well and start to see some of the ways you can be skeptical about the way it's being used. So, just a quick review of linear regression, and apologies for the, this should be showing a Gaussian distribution at the bottom. So I'll just sort of put that on what we mean by that on the visualizer. I'm getting good at this. So that thing at the bottom should read P of yi given xi is equal to a Gaussian distribution with mean W transpose xi and variance sigma squared I. And just as a sort of reminder, in statistics, we might think of this as a vector beta xi. This is an inner product, so it's equal to the sum of individual betas, beta beta j, xij, summed over j. It's just the inner product there. So it's a set of linear coefficients, which is determining the mean of a Gaussian. So the mean of the Gaussian is determined by a linear function, and the variance of the Gaussian is given by sigma squared. So that in matrix form has the following sort of shape, that y is equal to a matrix X that we think of as the design matrix, and we'll review design matrices in a moment, times a vector W. So this matrix X is, it's in the sort of real numbers, n rows and p columns. If we're using p, we could use d as well if we were being more machine learning. And the vector W, the number of parameters, which sometimes is denoted beta, is going to be p or d length, right? So the result of that is an n by 1 vector y, which is then, well, we can think of that as f, the prediction function, which is then corrupted by noise. So the expectation of the prediction, what we sometimes refer to as f, for each data point is just given by the inner product. Those two are the same thing. So what we do in practice, and I'm going to try and switch now to, and I've got it on this is called a comfort monitor. And now, having kept on turning around every other lecture to do that, I now know what it means by a comfort monitor. It's more comfortable to use it. So I've got the comfort monitor set up today, and there's this notebook associated, which is not an assigned lab, but it's somewhere to help you explore the different things. Now, we're doing the standard imports, but notice as well, we're going to import this library, stats models. So the stats models library is, I think it's basically giving you in Python some of the capabilities you would find in R with generalized linear models. I'd have to double check the history. I forgot to do that. But my expectation of the history is it's heavily inspired by what's available in R. So just installing those things, that'll take a little while. Where's it got up to? It is working away, is it? Oh, waiting to finish the current execution. Okay. Not sure why that's going slow. Let's interrupt and yeah, so I didn't restart the session. I might try, because it shouldn't have taken so long to run that first command. Let's try that. Okay, that looks better, doesn't it? Okay, that's still going slow. Connected to Python 3 compute engine background. Right, well, while it does that, I'll say what we're about to do. And again, apologies for my Gaussian distribution thing being messed up here, but wherever you see these blocks, that's what it's supposed to be. So what we're going to do is we're going to use stats models. So, you know, I think in some of the exercises, you've seen how to do this in linear algebra, but there's this nice package stats models that allows us to model these directly. Just going up here, that's a bit disturbing. Why is that doing that? Those already running. Runtime interrupt execution. Might just have to go to running it on my laptop. Right, 1 second. So I prefer to run it on the notebook because then I know that it's also all working for you. But in this case, I'll just run it on my laptop. Advanced data science notebooks. Okay. Right. Zoom in a bit. Okay. So those will be installed on here, but what I suspect is not installed on here is stats models. So now we're installing the stats models package, right? So it's got some dependencies, as you might expect. And what that's going to do is now allow us to do this fit directly. So it's very simple. Once we've loaded in the data, we've got a data input data X, a target value Y. And then what we do is we add a constant to X because X is just the times we're interested in, right? So if we do the regression without that, I'll show you what happens. So let's not add the constant and let's just fit ordinary least squares is what OLS stands for, with Y as the target and X as the input. And then we do the results. So what we see immediately is it's actually warned us. It's very cool. Since the model does not contain a constant, R is computed without centering. So it's warning us about a few things, and it gives us a load of statistics. So the R squared statistic, these are various information criteria that tell us things about model fits. Now, if we were in the stats department, you could spend an entire term course, teaching about just linear regression and what all these fits mean and how they should be interpreted. But what we've done here is just summarize what's going on. And these numbers will be a bit wrong because I've removed the add ones. But the model sticks, so a moderately strong fit with R squared of 0.744, indicating our model explains 74% of the variance in the data. And then there's a sort of check for overfitting, and that the model is like significant under some statistical test. The AIC and BIC values, look at them. They're really low compared to the ones we've got here, right? These are low AIC and BIC because I've removed that constant fit. And then it goes in to look at a few of the different parameters. But let's plot what that fit looks like. And find that we've got a little error. Probably if I do... because I removed the add ones, so I'm plotting the wrong thing. Okay. Oh, whatever the statistics look like, the fit is crap. And why is the fit crap? Anyone? This is a y equals mx plus c. And what have I effectively removed? C. So what's the intercept of this model forced to be? 0. So yeah, and look at the year, right? So where's it intercepting 0? At 0, yeah. So it's a very slow, I mean, so you can look at those stats all you like. You know, look at the plot. It's ridiculous, right? And the irony is when I was playing with this the first time around, I did exactly that error. So if you add in the constant, then you do the fit again. Oh. Are we getting the fit again? So the adding in the constant should allow us to have a better fit. Now, something's gone funny there. Because now I've forgotten to plot against the time value. Okay, so we add in a constant and you get something that's more like what you'd fit because you're in effect putting back in the C. But notice that C is coming in through, it's got one input, if we look at X, what we'll see is a NumP array where the first thing is all ones and then the second thing is all those years. But there's another of interesting things in here that it's sort of that we can sort of see do actually relate to our diagnostics. So looking at our plot and model statistics, we now can better understand the large condition number. So there's a large condition number. Large condition number suggests potential numerical instability or multicollinearity issues. So the condition number of the inverse that's going on while it's doing this, it's warning you about that. Why is the condition number large in this case? It's a straightforward linear regression, you might think. Why is the condition number large? What's causing it problems? And we can look at the plot. What might we think about the inputs in this case? What do we say about some of the things you have to be careful about with inputs? What are the values we're putting in here? So what are the numbers? Tell me the numbers that are going in as inputs on the time axis. They're years, Olympic years. So are they, what's the range where the computer operates best from a numerical stability point of view? With floating point numbers? Yeah. Are these numbers -1 to 1? No. So the scale of the numbers being large actually gives the model numerical stability problems. So it's actually fine in this case, but it would get bad if we would start doing polynomial fits. It's still fitting, right? That's not a bad fit, but you would start to get real numerical instability problems if you started using quadratic. And those statistics have warned us about that. There's other sort of interesting things, right? If we look at the data, we see the fit. There's this outlier. This turns out to be, this is a marathon running in the Olympics. This is 1904. It was held in America, and they had cars leading the marathon for the first time. Everyone got coated in dust. People got lost. You know, I can't run a marathon in this time, but Alan Turing would have won this marathon with his marathon time. And lots of people I know can run a marathon in this time. So it's a big outlier, which actually affects data. And some of the statistics are indicating there's outliers because when you look at the residual distribution, so the residual distribution being the difference between the prediction and these values, it says there's skew. The highly significant Jark-Berra test tells us the residuals are not normally distributed, right? And given the assumption in the model that we're assuming the noise is Gaussian, that can be a problem. So the skew and kurtosis values show the distribution is strongly right skewed with heavy tails. So strongly right skewed in a positive direction. Well, when we look at the plot, one of the explanations for that is this outlier, right? Skewed in the positive direction. But kurtosis means heavy tails. So high kurtosis, low kurtosis means light tails. So that's what we call super Gaussian tails. So Gaussians have relatively light tails. They don't expect things to happen a long way away from the mean. It gets really improbable very quickly. But for a high kurtosis, it's a so-called heavy tail distribution, meaning you can get these big outliers. So it's about trying to explain, so what the residuals, when you look at the residual distribution, what it's saying is, look, this distribution with this thing here is causing me to think that there's strong kurtosis and strong skew in this tails. So the residuals are non-Gaussian. So that's another warning that there's something funny with your model. So let's have a little play by introducing design matrices. Again, apologies for the design matrix. I can just do that for the moment. Or another way we would often, the reason I have it defined is like that. That's very common. Oh, where did that go? So that's very common as a representation of the design matrix, and X, capital X as well. So in the design matrix, what you sort of start to say is you have multiple features associated with every data point. So we can think of those as X's or phi's. And then we put those features along the rows, and then each separate data point goes in the columns like this. Oh, wow. So what we're going to do now is we're going to build a matrix that takes in our knowledge of what was going on in the world across these Olympics to try and get a better fit, right? We're not going to deal with the 1904 St. Louis Olympics. We could fix that in a moment. But what I've set up here, first of all, scale the year to avoid numerical issues. So this scaling is an interesting choice, right? There's a number of things one might imagine doing, right? You might imagine just looking at the variance of the input value and scaling it down to be variance 1. That would be a perfectly sensible thing to do. One challenge with that is your coefficients will have become quite difficult to interpret because they're downscaled. So if you don't scale, it's like the coefficient is giving you a per year, like change in performance time, because it's a linear model per year. It's got an interesting thing. Now, by scaling in this way, centering it at 1900, so the intercept is actually for a year that we understand. So the intercept will then suddenly be telling us this was the performance we expect in the year 1900, which is a much more reasonable year to think about than the year that was apparently the year of Christ's birth. I mean, I think we're less interested in how fast the disciples would have run the marathon than we are how fast people ran it in 1900. And then scaling it by 100, it's not going to give us exact between -1 and 1, but it's meaning everything is like change in pace of the marathon per century. That's how we interpret the thing. So that's a sensible, interpretable thing to do that is going to get us down to a nice sort of range. And then look what we're going to do here. We're going to augment. So that's the scaled input. And this is the augmented design matrix that we're building here. And we're going to augment the design matrix with some indicator variables. So what is this doing? This is saying if the year is under 1914, so if it's pre-First World War, add an indicator variable, add 1 to the design matrix, right? Then we're doing the same thing here. If the year is across the world wars, add a second indicator design variable. So if you think about what we're constructing in the design matrix here, we've sort of got 1896, 1900 going down from the first Olympics. And then what we're saying is, oh, this first column is it's pre-First World War. So up till 1914, this is 1, and then it goes 0, 0, 0. And then the next column is 0, 0, 0, 0, but then is 1 for it's across the world wars. Yeah? And then there's a third column that we're going to put in for after 1945. So what happens after the Second World War, a third indicator variable. Let's just have a pause and think about what that's going to do. Well, if we just leave it in there, what does it enable the model to do? So ignore this additional line here and just think about these constant terms. How many additional parameters is that going to give us in the model? 3 more parameters, yeah. And what will each of those parameters represent? Brilliant. They're going to represent a shift in those periods. But what if this is modeled just by a shift, but it's best modeled by a shift and a gradient? Well, then that's what this line is doing. It's saying, takes those scales and multiply the first scale, the scale time, by the first augmentation, right? So what these things are doing here is they're then saying, okay, across those constant things, multiply by the time. So they're actually a polynomial term. They're now multiplying some of these features. So they're giving us an additional separate feature, which is of the form 1896, 1900, 1904, 1908, that'd be 1912, wouldn't it? And then 0, 0, 0, 0, 0. right? And then the next one's going to give us 1914, zeros down here, because by multiplying by those things, it's just zeroing out the areas where there's time. So now what that allows to happen is it gives us a couple of additional parameters. And those additional parameters, and I think if I look here, I realize I'm missing one, I think. Unless I've misunderstood what I'm doing here. Those additional parameters are then going to give us the ability to have an M for each of those zones, right? So 3 more parameters, which is going to sort of mean that we can actually change the gradient at each time. So let's do that. Oh, and then realize we haven't imported NumPy. And now look what happens. Okay, this is interesting. The smallest eigenvalue is, this is of the posterior covariance, is basically 0. Why has that happened? Multicollinearity. Okay, what we've done by creating ones, and then another set of ones for the post-war, and then we have the original set of ones at the beginning, and then by also recreating all these times across these different periods of time, we're effectively doing something slightly odd, which is replicating the data twice. And that's why the smallest eigenvalue is 0. And that will lead to challenges in the model that mean that, first of all, you're fitting a constant for everything, an intercept for everything. That's just sort of C0. But then you're fitting a C1 as the intercept for the pre-war, a C2 for the intercept of the across the wars, and a C3 for the intercept after the Second World War, right? So you could, in effect, C0 is actually scaling all those. So there's a parameter on identifiability if we do it that way. So let's reverse out of that and say, okay, well, what happens if we don't do the post? So here's the trick. We don't do this one. We simply do the previous ones, right? So we basically allow one full linear regression for everything, which is going to take account of the post-Second World War, because that's the regime we care about. And then modifying, you're allowed to do modifiers for the linear regression for pre-First World War and post and across the wars. Does this make sense? All within the same model, right? Because these things are all being added together. In effect, what we're doing is F1 plus F2 plus F3, where F1 is like a regression that is only being applied to the pre-First World War. F2 is a regression that's being applied only across the wars. And F3 is a regression that's being applied globally. Yeah? So F3 is going to be dominated by the behavior, the outside, the residual behaviors from these other regimes are now going to be mocked up by F1 and F2. Let's hope. Let's see what happens. Okay, look at the condition number now. Yeah? It's beautifully conditioned. So that was the problem, right? And it's no longer warning us about the condition number. And there's the fit. So this is some kind of piecewise linear fit now. And if we look at the coefficients, so we now have all these different coefficients which are associated with however we've set these things up. So the last one that we added was the, so how have we added, what order have we added them in? So the first one is the scaled time, but then we add a constant at the end. So it's augmented with a constant. So you get the possibility of, you can see all the coefficients here, and there's various statistical tests around them. Now, like I say, we could spend an entire term teaching about these statistical tests, but I think the really interesting ones are the residual plots. Let's see if we can just have a plot of the residuals of the two things. So again, doing this live, so you can watch me mess everything up. So the prediction results, let's rerun this because otherwise we'll pick up the prediction results from below. Aren't notebooks fun? So the prediction results are in the form results predict. And the original is in the form of y. So PLT hist. Oh, so that's something wrong with that, isn't there? Because it's let's just have a look at what's wrong with that. Okay. What's wrong with that is, you see, who saw what happened there? Classic Python annoyances. So I always do everything in so let's get back to what we had before. So results predict are in this form, but when I do this histogram, something went wrong, and I get a result that's in the form of a matrix. Anyone know? I mean, this is a constant horror when you're playing with things in Python. Anyone notice why has that happened? I can't remember what they call this in Python. This has happened. Does it give you a clue if I just show you the form of y? Yeah. So Python now says, oh, obviously you're trying to subtract these things in this way, and silently creates this enormous matrix, rather than what MATLAB would, for example, do, would say, oh, I can't subtract those, they're not matching dimensions. And it's useful in Python because this allows you to create such things without scaling up memory. What's it called again? Oh, what's the name of it? Broadcasting. Yeah, thank you. Yeah, Python's broadcasting, whereas MATLAB wouldn't, for example. I'm not sure what R would do in this case. So the reason that went wrong is because it broadcasted it. So I think I can fix that with flatten. I find this really irritating because I like to have all my data matrices in this form, so that the first dimension is always the data point and the second dimension is a data feature. And it's something I find very irritating about the way they set up Python. And it actually shows something which I think is true. You know, NumPy was not designed by people who understood numerical analysis very well. I mean, you know, I'm sure they were fine, but they weren't experts in numerical analysis. So let's try that now, if that's going to be a bit better. Oh, so okay, so we need a few more bins, it looks like, doesn't it? Is it n bins? 100 or bins. There we go. Oh, that's too many bins. Makes sense, given I only had 20 data points. So let's try 20. So there's not a lot of data to sort of see the histogram of these residuals, but you can at least see that enormous outlier, right? Yeah. There's another thing that I don't know why it used to have, like width equals, again, let's test if I actually remember that. Oh, no, I don't remember that. It used to be a way of setting the width so that the histograms are a bit separated, but I can't remember how you do that. So these are all the sort of things you do. Look at residuals, try and histogram the residuals. If you've got a lot of data, the histogram's really, really informative. But basically, these residuals aren't very Gaussian still. Let's see if they look much different with the other one. Go down below. Oh, what have I done wrong now? Oh, model predict. Model predict is not based on X, is it? It's XORG. Okay, so that's interesting because we still sort of have the outliers. So let's just go back and check the kurtosis and things it's sort of it's talking about. Anyone see where they are? Skew and kurtosis. Yeah, there's still quite a high skew and kurtosis, right? So it's also recognized even with this one, with this greater linear fit, that's not dealing with the residuals. The residuals are still non-Gaussian. So that still tells us, in some sense, the Gaussian noise is not the right form of noise. That can be deeply problematic when you've got outliers, because the Gaussian is very sensitive to outliers. It pulls you and skews you in the wrong direction, right? So these are all how you are skeptical about your fit. These are all indicators that say, well, hang on a minute, have I got this right? Is this a robust fit? Whatever. And the type of things you can do is change the nature of the model. You can definitely do a sort of models with non-Gaussian noise. They're still generalized linear models, but you can also try adding features, moving the features around. One of the parameters was whether the model was overfitting or not. So what parameter was that? This is Durbin-Watson statistic indicates positive autocorrelation. Yeah, what does that mean? Positive autocorrelation in the residuals means that they're not independent, right? Yet our model is saying they're independent. And so it's saying, well, consider maybe it's a time series. Maybe you need polynomial terms, right? And of course, this is the one we did. There are different eras in marathon times. So that's what we fixed it up for. There was one other said that was about the whether it's overfitting. Oh yeah, the adjusted R squared of 0.733 confirms this is not due to overfitting. So let's check whether these statistics show that our models overfit. The adjusted R, no, again, it's not overfitting, right? We're getting an R squared, which is higher. We're explaining more of the variance, 87% of the variance, but the model still thinks it's not overfitting. And, you know, we can also eye that in this one dimension. You can look at that by eye in one dimension and see that that doesn't feel like it's overfitting. Okay, so that's linear regression. Let's go back to, as a sort of reminder, and what's going on with generalized linear models. So that's sort of what we've been just reviewing there, design matrix. Okay, generalized linear models. So in the regression, we're modeling the probability of Y, the output directly. Now, what we can do is we can go to the framework of generalized linear models and allow us to model it indirectly. So one of the things we talked about in the example at the very second lecture is if I want to model the probability of someone buying a jumper or not, then instead of modeling that probability directly, I can model the log odds of the system. So what we do is take the probability, and instead of modeling it directly, we look at the odds, the probability of it purchase occurring over the probability of purchase not occurring. And then we take the logarithm to map those between minus infinity, infinity. And then we end up with the logit function. And in generalized linear models, this is known as a link function. So what we do in generalized linear models is we end up, instead of saying that the output we're interested in, which previously was Y, is equal to some linear over X, what we say is that the log of the probability of positive over 1 minus the probability of negative is equal to W transpose Xi, right? Now, this is how they do it in statistics, and it's nice in the following ways. It allows us to do things like, well, we're decomposing this such that it's going to be, well, let's do it in the statistics notation, beta 0, some intercept, plus beta 1 times feature 1, plus beta 2 times feature 2. And take, for example, Q risk, which is the score that's used to determine whether people are likely to have high cholesterol. The Q risk score, these parameters become important because these are things like, has the person smoked before? Are you a smoker? They're like indicator variables of that form. This one's like, oh, how much do you drink? You know, and then another one is actually your cholesterol level or something like that. And so you can see which of these factors are relevant in predicting risk of heart attack, which is what Q risk tries to do. And that's sort of very nice, but be careful because you are not directly predicting the odds, right? So here's another way of writing this. Pi I over 1 minus pi I is actually equal to the exponential of W transpose X. which means it's equal to the product of exponential of, if we switch our notation to beta, of over j of beta j times xj. So this is a product model. It's not a sum model. When these things are being accumulated by the model, they're being multiplied together. And so that's one very misleading thing about this way of writing it down. If there's a logarithm there, it's not an additive model, it's a multiplicative model. And that can be very misleading. Does that make sense? Because what you're saying is the odds are driven by a product of these things, where each of these terms is a positive term. Yeah? So it's a log additive model, which means it's a product model. And that's something I think that people slip up on all the time when playing with these models. Now, what we tend to do in machine learning is we tend to write these models the other way around, which makes it very clear what's going on. We tend to write the model in this form, which in some ways is a better form of writing the model, which is we invert that link function. And if you invert that link function, then what you find is that this is the model you're interested in, where that could also be beta. And this is recognized as a sigmoid function that you'll see all over neural networks. So what it's sort of saying is that your f is coming through a sigmoid function. And all machine learning people will write it in this way, which has the advantage that you're sort of seeing that there's a non-linearity around where these features are, but it is a generalized linear model, right? If I made this a neural network, that's not a generalized linear model because this function would not be a linear function, right? The generalized linear model has a link function around. In a neural network, this would be multi-layer nonlinear function in the parameters, but it's a generalized linear model because this function's a linear function, okay? So that's the logistic, and it comes about by inverting things around, so we're predicting the probability directly in this way. Here I've used phi as the basis. I'm using them interchangeably for the design matrix. Now, how do we fit this? Well, so this is our model for pi. This is our prediction function. So this is basically saying we've got a model, pi of x, that is 1 over 1 plus e to the minus w transpose x, right? That's our prediction function for the probability. But the way we fit this in practice is we need to turn it into a likelihood, or this is the probabilistic view on things. And what we use is we use the Bernoulli distribution, which is a really simple mathematical trick. So bear in mind the targets here are always 1 or 0. So all this distribution does is if y is 1, it switches pi I on to be the answer. And if y is 0, it switches 1 minus pi I to be the answer. So it's kind of this in code, right? But that's how you write this thing. It's just a mathematical switch, right? You use this trick a lot in machine learning, that you can basically use the 0 or 1 to switch in the thing you're interested in. It works, of course, if the different values of y are only summing to 1 in total, right? The same thing happens in multivariate if you have more than one output, so multinomial distribution. And then once we've got that, you can just do maximum likelihood. And that's how we fit these non-linear versions. So it's exactly the same as the linear regression, where you do maximum likelihood of the Gaussian, which turns out to be a least squares problem. But in this case, you do maximum likelihood for these things. And here's the form of your likelihood now. So the form of the likelihood, the log of P of y given x is equal to the sum of yi times log pi. Now, yi is either 0 or 1. So basically, if this is positive, you have an input that's log pi I. If it's negative, you have an input that's log 1 minus pi I, right? And of course, the log of that is just as defined. It's the log of the sigmoid, right, of wx. Now, once we substitute those things back in, we can write things down in terms of these parameters. And then you can optimize by taking gradients with respect to pi. So the gradients with respect to the prediction function, which are of this form. Of course, nowadays, that's all done if in modern machine learning packages with automatic differentiation. But in the old days, that would be manually written out and all the gradients would be computed. And you substitute in the objective, and then you do some form of optimization of the function through Newton's method or gradient-based optimization. So unlike the linear regression, which is for small models, at any rate, just a direct application of linear algebra, here you have to have iterative approaches to find the fits. But the nice thing is that stats models will do all that for you, right? So behind the scenes, in the notes for this, which I won't go through now, but in the notes for this, you see what I've done is, oh, sorry, go back there. I've actually set things up so that to show you what's going on, right? This is the objective function. This is me writing it all out manually. This is the gradient of the objective function. And then this is then fitting that to a data set of that was developed in Cambridge, like a long time ago when it was actually quite rare to be able to digitize people, that classifies people as wearing glasses or not. So there's something wrong in there, but this basically just does gradient-based optimization, and then also looks at stochastic gradient descent as an alternative. But like I say, you can just do this with stats models. So in this case, using logit instead of OLS. Yeah, so that's telling you what the link function is. As a final domain of interest, you can also do things like Poisson distributions. Who knows what the Poisson distribution is? Heard of it before? It's like a count distribution. Yeah, it's very cool and used a lot in like network systems. It has all these interesting properties, including this memoryless feature. My favorite way of thinking about the Poisson distribution is imagine a setup where in every minute, there's a small probability of something happening, right? And so like it's like 0.001 or something like that. So over time, in any given minute, things are unlikely to happen, but as time accumulates, eventually something happens. Now, if you take that time and that probability and you close down that length of time while decreasing the probability appropriately, then you get the Poisson distribution in the continuous limit. So it's basically sort of really an interesting, if you believe, for example, in a football match, that goals are scored with equal probability throughout the match, they are not. But if you believe that, then Poisson distributions are interesting models of what's going on, right? It turns out there's all sorts of interesting correlations in football match and other sporting events. And so Poissons are defined by rate parameters, and this rate parameter lambda is now the thing that we would do the prediction with. But again, the rate parameter has to be positive. So what we do is we define the log. We use a log link function, and we say that the log of the parameter is equal to the sum. So once again, be careful, because what we're saying is the rate is a product. Yeah. So the log of the rate is a sum. So the rate itself is a product of different influences. And then it's slightly annoying. I used to have this example which downloaded Google Trends data, but they've somehow blocked the API I used to use. This is one reason why I've really, across my life writing lectures, I've gained a very large distaste, he says, for Google, because they constantly change their APIs. And you know, if you're lecturing your API, you only look at your API once a year maximum when you're trying to update your lectures. And it's what a nightmare to have to rechange everything. So Google Trends is one of the things I'm afraid we've lost. So I used to have these examples where you download data from Google Trends and then try and fit the data with those. But now we're just going to do a simulation example. So we're just going to generate some counts and then fit the counts with a GLM. But now what we do is we're doing explicitly. Before we were using like logit or OLS, but here notice we're specifying the Poisson family in that way. So we're going to do a fit, and it's done the fit for us. Again, this fit is being done numerically. You can't do the fit directly, but what we're then showing is a couple of sensible diagnostics plots. So here's the residuals plot, and here's an actual versus a predicted plot of those two. That's good. Yep. So you can do Poisson fits with these things as well. And that's the beauty of generalized linear models. You've got all these different fit forms. So where should we get to? So in terms of what we're doing when you're doing your lab, oh, get back to my slides here. So, practical tips. When you're fitting these models, the feature engineering is crucial. And a lot of this is where you're going to be at this interesting boundary between address and assess, right? Because your features are what's in the data, and you've been assessing them, working towards that. And then downstream, you might find out something more about your features being incorrect. But what we'd like you to do is when you go back to do assess, it's sort of this iterative fractal recursive type process. You then go back in and change the feature pipeline to ensure these other features that are available or whatever else. And because someone else might want to use those features for something, it's not just for the question you care about, but you will potentially find out that you want to go and get some other set of features because the quality of your model isn't what you thought it is. But just keep trying to structure things in such a way that anyone else could also pick up your assess software and use that to get their own features. And that's what I mean about building modular pipelines to test these features. So one of the things you'll also find as you go through this type of thing, you're like, oh, you start playing with it a bit like I was playing with things here, but try and look for patterns and structures in the way you're testing things so that you can do some more exhaustive testing or exploration in such a way so that when you go back and do the features, you've still got code that means you can run your pipelines and do the testing. Structuring things in that way is useful. Consider interactions between variables, and that can come up in multiple different ways, right? So we created interacting variables that allowed us to do linear fits in different regimes, but in doing so, we also caused numerical instabilities in our fit, right? We ended up with a covariance of the system being numerically unstable, having either an eigenvalue that was low, or when we failed to scale our years, we also had stability issues, right? So these are all the sort of things that you're doing in practice, scaling your inputs to be within a reasonable regime, checking you haven't over-parameterized the system. And then document your process carefully. Now, what do I mean by this? Well, the person in some sense you're documenting for is yourself in 2 years' time. When you come back to this analysis and what on earth was I doing here? You want to be able to get up to speed on it, right? And by documenting for yourself in 2 years' time, you will find you're also documenting for other people. So when I say carefully, I don't mean, oh, every time you're doing something, document the whole thing. I mean, just put this information that you need in there, perhaps in bullet points initially, but then go back and as you sort of doubling down on an approach, try and improve the quality of the documentation. We'll be looking for that on the practical. There are various other validations we didn't talk about today, but you will have learned about in your previous machine learning courses, which is things like using cross-validation wisely. Bootstrap sampling, if you haven't heard of it, is a very cool way of evaluating uncertainty. Only works for small data sets. You might not be able to use it. If you're doing larger data sets, you can keep out holdout test sets to validate what's going on. And temporal leakage is this thing of if you're fitting things across time, you have to be careful about cross-validating isn't telling you what's going on. You have to be careful about how that's working. And then all the other bits and pieces we were looking at, residual plots, nonlinear patterns in those residuals, such as the kurtosis, the skew, and try and identify influential points like the 1904 Olympics. All of these things are things that you should be bearing in mind while you do the analysis. So Visualization, remember to plot the raw data and create diagnostic visualizations and check the model assumptions. So stats models is doing that for you, right? Doing a whole load of that. And you can easily look up what those statistics are. That's the sort of thing we're interested in for your final result. What work have you done to justify the decisions you're making? We're constantly looking for this healthy skepticism that the data scientists should have. And these are ways you can show that healthy skepticism, right? Okay. And so I think that's it for today. Unless any quick questions. Anyone? Or comments? Or any comments about the